This is when we're setting up our dimensional analysis equations. So let's go ahead and look at the first example. So the first example, we're going to predict the mass of the products. And the question reads, what mass of water is produced when 246.4 grams of methane is burned in excess oxygen? So there's a few steps we want to take to solve problems like this. The first step we need to write a balanced chemical equation for the word equation in the problem. So we have, in reading the question, it's saying what mass of water is produced. So we know water is produced when methane is burned in an excess of oxygen. So methane is going to be one of our reactants. So we're going to start with methane, and it's burned in an excess of oxygen, so plus O2. And now we know that one of our products is going to be water. And when we go ahead and solve this reaction, we know that the other product is carbon dioxide. And we know this because we have carbon on the left side of the arrow, so we're going to need it on the right side of the arrow. And if we look, the elements we have on the left side are the same as the elements we have on the right side: carbon, hydrogen, and oxygen. So now that we have the equation for the question, we need to balance it. The first step is always going to be to balance our equation. So remember from one of the previous videos, we split the equation in half at the arrow, and we write all of our elements on the left side of the arrow underneath the line. So we have carbon, hydrogen, and oxygen. And then we're going to count the atoms that we already have for these elements on the left, and then we're going to count them on the right. So on the left, we have 1 carbon, 4 hydrogen, and 2 oxygen. And on the right, we have 1 carbon, 2 hydrogen, and 3 oxygen. So now in order to balance the atoms of each element, remember we add coefficients to the front of the compounds within the equation. So carbon is already balanced. We're going to look at hydrogen. So we always go to the side with a smaller amount of hydrogen. And when we're looking, the right side has 2, the left side has 4. So we're going to go to the right side, and we're going to add a 2 in front of the water. Now that 2 is going to change how many hydrogens we have. So we cancel out 2. We now have 4 hydrogens. However, that 2 also changes how many oxygens we have. So the new amount of oxygens, we have 2 right here and 2 over here. So now we have 4 oxygens. So our carbons are balanced, our hydrogens are balanced, our oxygen is not balanced. We go to the side with a smaller amount, which is the left side, and we want to get 4 oxygen atoms. So we're going to put a 2 in front, and that's going to change how many oxygens we have to 4. So now we have a balanced chemical equation. So I'm just going to rewrite the equation so you can see it more clearly. So we have methane plus 2 oxygen. It's going to give us 2 water plus carbon dioxide. Okay, we're going to use this balanced equation to then calculate the mass of water that was produced in the reaction. So when we're doing stoichiometry problems, there's when we set up the dimensional analysis, there's a way that we set up the analysis. So remember from regular chemistry, we always start with the number in the problem. So they're giving us the mass of methane. So when we want to find the mass of water, we're going to start with grams of methane, and we're going to have to convert that to moles of methane, which we are then going to convert to moles of water. Sorry, I'm going to go up a little bit. And from there, we can go to grams of water. So this is going to be the approach we take in our dimensional analysis to get us from grams of methane to grams of water. We can't just go straight from grams to grams. We have to convert each compound to moles, and we're going to go from grams of one compound to grams of another compound, first stopping at the mole. So the way we're going to set this up is we always start with the number in the question. So we have 246.4 grams of methane, and we want to convert this to moles of methane. So in order to convert it to moles of methane, we set up our first fraction. Remember, whatever unit we start with is the unit that goes on the bottom. So we started with grams of methane. So grams of methane is going to go on the bottom. And when we have grams inside of our fraction in dimensional analysis, we always put the atomic mass. So the mass of methane is 16.04. Sorry, it's hard to get the decimals to show. And on top of this fraction, we're going to have 1 mole of methane. So right there, we just converted to moles of methane. Now we have to convert to moles of hydrogen. This is where we go from one compound to another compound. So because we have 1 mole of methane up here, we need to have moles of methane on the bottom so that in the next fraction so that they cancel out. So on the bottom, we're going to put moles of methane, and on top we have moles of water because that's the compound we want to go to. Now, when we have a mole to mole ratio in our fraction in dimensional analysis, we always get those numbers from the balanced chemical equation. So from this balanced chemical equation, we're going to get the numbers to put inside this fraction. So the number we put in front of H2O would be the coefficient in front of water in our balanced chemical equation. So we're going to put a 2 in front of H2O. And the number we put in front of moles of CH4, again, is going to be the coefficient in front of CH4. Since there is no coefficient, we just put 1. Now, in that step, we just converted from moles of methane to moles of water. We're going to set up our last fraction to now convert from moles of water to grams of water. So because we have moles of water up top here, on the bottom of our next fraction, we also want moles of water because remember, we want our units to cancel. So we're going to have moles of water right here. And because we're converting to grams, on top, we're going to put grams of water. And remember, inside our dimensional analysis fraction, it's always going to be 1 mole. And how many grams of water are in 1 mole? We're going to calculate the molar mass. So the molar mass of water is 18.02. Remember, we get the molar mass from the periodic table. We're going to take the atomic mass of all of our elements and add them up. So now we have our mathematical equation to get from grams of methane to grams of water. And remember, when we're solving these equations, the easiest way to do it is to multiply all of the numerators together and then multiply all of the denominators together and then divide your answers. So when you do that, the answer that you should get for this problem is 553.6 grams of water. And that's how we set up our stoichiometry problems when we're going from grams of one compound in the reaction 2 grams of another compound in the same reaction. So the next problem I want to look at is predicting the mass of 2 products. So we're going to set it up the exact same way. It's just that we're going to have 2 equations now. So remember, first, we have to write a balanced chemical equation. So the question reads, how many grams of carbon dioxide and iron are produced when 114 grams of carbon monoxide gas is added to a vessel containing excess hot iron 3 oxide? So when we look at the problem, we know that our products are going to be carbon monoxide and iron 3 oxide. So when we write that out, our equation is going to be iron 3 oxide plus carbon monoxide, which is going to give us carbon dioxide plus iron. So this is our chemical equation, but now we have to balance it. So again, we split it down the middle. We write all of the elements we have on the left side, oxygen and carbon. So, and then we count how many atoms of each element we have on the left and how many atoms of each element we have on the right. So for iron, on the left, we have 2. For oxygen, we have 4. And for carbon, we have 1. And then on the right side, for iron, we have 1. For oxygen, we have 2. And for carbon, we have 1. So clearly, our equation is not balanced. So we're going to add coefficients in front of the compounds to balance the equation. So let's start with iron. We have 2 on the left, 1 on the right. We always go to the side with a smaller amount. So we're going to go to the right. We want to make it 2. So we put a 2 here. That changes how many iron we have to 2. Now, let's go to oxygen. We go to the side with a smaller amount, which is the right side, and we want to try to get 4. So we're going to start by putting a 2 right here, and that's going to change our oxygen to 4, and it's going to change our carbon to 2. Now that balances our oxygen, but it doesn't balance our carbon. So when we go through and try to balance our carbon, the easiest way to do this is if we put a 3 right over here. That's going to change our carbon to 3 and change our oxygen to 6. And when we go to the right side to try to balance it, instead of having a 2 here, we're going to put a 3. And that's going to change our carbon to 3, and it's going to change our oxygen to 6. Remember, balancing chemical equations is trial and error. So you're just going to try some numbers and keep going until you see which ones work. So now our balanced chemical equation looks like this. And remember, these coefficients are what we're going to use in our stoichiometry problems to go from grams of one substance to grams of another substance. So we found the balanced chemical equation. Now we need to find the masses of carbon dioxide and iron. So we need to find the masses of both of our products. So because the problem gives us 114 grams of carbon monoxide, that's how we're going to start both of our stoichiometry problems. So first, what we're going to do is we're going to go from carbon monoxide, because that's what it gives us in the problem. It gives us carbon monoxide. So we're going to go from carbon monoxide to carbon dioxide. Then we're going to set up a different problem. We're going to go from carbon monoxide to iron.